Screen now. Okay, so today's lesson is topic 8 and 18, that's acids and bases. And the first part of this we're going to focus on is the SL aspect of it. Okay, mostly conceptual, a few calculations here and there, but overall it's more about understanding how acids and bases react and how they behave, and then the real life applications for them. And so the first thing you want to establish is the definition that we use for all of standard level acids and bases, and that is a Bronsted-Lowry definition. Okay. Now, the HL section has another definition called the Lewis definition that we will talk about in the HL section, but for SL, everything is related around the Bronsted-Lowry definition. Okay. And so we have a Bronsted-Lowry acid that's defined as a proton or an H plus donor, and a base that is a proton or H plus acceptor. Okay. And like I said, I'm going to combine a couple of different ideas here as well so that we can kind of cover a lot of ground. When an acid does donate its proton, it becomes a conjugate base. And when a base donates accepts its proton, it becomes a conjugate acid. Okay. And those two species are in tandem considered what's called a conjugate acid-base pair. I make the pause between conjugate and acid because I want to make sure it's distinctive that the word conjugate is not paired with the word acid in this term. It's conjugate, acid-base, and then pair. And so when you look at a reaction for a Bronsted-Lowry definition, you should see the movement of one H plus from one species to another. So you might see something like this. NH3 plus H2O yields NH4 plus OH minus. And we'll talk about the arrows in a little bit when we talk about strengths of acid bases, but this is the appropriate arrow for this. In the reactants, you can see that the H is being donated from the water to the NH3 to form NH4 plus, which means that NH3 is our Bronsted-Lowry base, and water is our Bronsted-Lowry acid. Now, the results of this reaction produce our conjugates. And so what happens here is our NH3 produces our conjugate acid. And our acid produces our conjugate base. Okay. And a conjugate pair should only differ by one H. So you can say that NH3 and NH4 plus is a conjugate pair, and also H2O, bless you, and OH minus is also a conjugate pair. So both of these are considered conjugate acid-base pairs. Yes, sorry. Yes, Marina. Yes, yeah, I know what you're trying to say. They should be very, very similar in their formula, correct. So it shouldn't be like NH3 and OH or something like that. They should be very, very similar, only differ by an H plus. Yes. Okay. So yeah, like that distinction here, the chemical formulas should be almost identical except for one H plus. And yeah, correct. Sure. So what you want to imagine here with this, Camilla, is that if you treat it as a reverse reaction, like if you read it right to left, the opposite's going to happen, right? So like if you read it right to left, what's happening here? This H is going here, right? So this is our conjugate acid. This is our acid on the right side, and it happened only because it came from the base. Does that make sense? Yeah. If the conjugates are like, what would happen in the reaction in the reverse direction if you were looking at an overall reaction? Well, you have to look at whichever one's giving it up to look at the other side. So like look at what results on the other side, and that should tell you. So in this case, because NH4 plus goes to NH3 in the reverse reaction, that tells you NH4 plus is an acid. So yeah, not necessarily the most H's. Okay. You may also be tasked with predicting conjugate, okay, predicting conjugates. So this is a little bit, I guess, quote unquote, tricky, but you have to think about it in terms of what is it producing and where did it come from. So if they ask you, like, identify the conjugate base of HF, okay? Now, if you're looking for the conjugate base of HF, that means HF acts as a what? A donor, proton donor, yeah, sorry, an acid. I was looking for acid, but proton donor is the same thing, correct. So the HF acts as a proton donor or an acid, so therefore the conjugate base would be what's left after you donate that H plus. So the conjugate base would be F minus. Okay. Conversely, if I ask for the conjugate acid of, let's say, water, that means water's acting as a base or accepting a proton, which then means that the conjugate acid would be H3O plus. Okay. Now, if you notice, in our examples, water has been able to act as an acid or a base, okay? And so water can donate and form an OH minus, or can accept and form an H3O plus. And this term is amphiprotic, okay? Do not use the word amphoteric. Amphoteric is for Lewis definitions of acids and bases, not for Bronsted-Lowry. So SL, you should never worry with the term amphoteric. You should only worry about the term amphiprotic. Yes, Marina. Amphiprotic. So, like, you should use the term amphiprotic when you're talking about something that can act as an acid or a base. Yeah. So, an amphiprotic can act as a Bronsted-Lowry acid or base. Okay. Because think about it, Bronsted-Lowry's definition has to do with protons, and hence the term amphiprotic, because protic means protons, amphi means both directions. So you can both give or receive a proton, hence the term amphiprotic. Other species that can kind of be grouped in here are usually kind of like ions of acids and things like that. So like something like HSO4 minus could reform H2SO4, but it could also form SO4 2 minus. So the ability to gain or lose a hydrogen. Now, you don't want to start with an acid and then assume it can gain another hydrogen. That's not how it works. Usually it's an acid has more than one H and it's lost one already and then can regain it to return to that form. So like HPO4 2 minus is also that, because you could go to H2PO4 minus, or you could lose another one, become PO4 3 minus. So there's several different examples of amphiprotic species that I wouldn't memorize them, but do be able to recognize, can it gain or lose a hydrogen? Yes, Marina. That's a good question. I would say this, okay? Other than water, How do I want to say this? Generally speaking, other than water, you you can't accept a hydrogen that makes you into an acid. Oh gosh, that's a weird kind of trick. I'm trying to make a statement here because like I kind of want to say that if you add an H to a species that is already neutral, it's usually difficult to make it to accept it, but there are exceptions to that. I don't know if there's a specific way to identify. Yeah, yeah. Sorry, I'm thinking about that because I want to see if there's a way to simplify it. But if it's an acid, it should not usually be able to go positively charged. I think that's a safe bet. So if you see something like HCl, it can't go to H2Cl. Or if you see like H2SO4, it can't go to H3SO4. Bases can become positive, but acids can't. So if you have a species that, okay, that's an acid, but it already has the maximum number of hydrogens, then it can't accept another hydrogen. That's the best way to do it. Okay. So like, yeah, so like kind of answering Marina's question. So if you see something like H2SO4, it can't go to H3SO4 to, I mean, 1 plus or something like that. That can't do that. The acid is the maximum number of hydrogens it can accept. So don't try to put a positive charge on it. That's a good question. Okay. Questions about that? Okay. See, I don't like the order in which they do this. Okay. Actually, no, we can do that. Yeah. Okay. Okay. Acids have a variety of reactions that you have to know that they can react with, and most of these are single displacement. So hopefully they're not really like necessary for you to memorize them completely. But you need to know how acids react with certain things. And so I'm going to stick with HCl as my example for my acid for each of these reactions. But so you have to know one, how they react with reactive metals. So that's usually our group 1 or 2 metals. And in this case, it's going to be a single displacement reaction. Because what happens is it produces a salt and a gas. So you should be able to observe bubbles forming when you mix these two together because you're releasing hydrogen gas. You should also be able to react with metal oxides. Actually, since we're doing review, I'm just gonna kind of lump a bunch of things here as well. Metal oxides and hydroxides, okay? Because they really behave the same way. So you might have HCl reacting with a metal oxide like Na2O, okay? And you end up getting kind of a double displacement reaction of NaCl plus H2O. And you have to balance this as well. With hydroxides, you still form the salt and the water in those reactions. So metal oxides and hydroxides form water and then the salt of the other 2 ions that are in there. Like in the sink?
Yeah, like doesn't turn on.
Okay. So metal oxides and hydroxides is salt and water. 3. Hydrogen carbonates and carbonates. Okay. So with this, it is still kind of the same reaction as metal oxides and hydroxides, but you get slightly different products. And you do need to separate these products apart or you won't get full credit. So HCl reacts with both. And a hydrogen carbonate is something like a salt with HCO3 minus in it. That's one of the polyatomics you have to know. Carbonate is also a polyatomic you need to know, CO3 2 minus. And so while this is a double displacement reaction, you combine the K with the Cl, and they're both +1 and -1 charge respectively, so therefore it's a 1-to-1 ratio. The other product you would expect to be H2CO3, but what you have to know is that H2CO3 breaks up into water and carbon dioxide. And you are not awarded full credit if you write H2CO3 as your product. You have to write it as CO2 and H2O because one of the characteristics of this reaction is a gas being produced. And that gas is CO2. So if you write it as H2CO3, you don't have the production of gas because H2CO3 isn't a gas. And so that's one of the reasons why the IB is really a stickler on that. You need to write it as H2O and CO2 so you can know that you should be observing a gas produced.
So we don't write it as H2.
No, correct. Do not write it as H2CO3. Marina.
So like you should never get H2CO3 as a product.
Correct.
And this acid is a basic.
Unless your reactants are CO2 and H2O, and that's the only thing you can make, then yes, you should never get H2CO3 as a product. Yes, Alexander.
So you're just using HCl as an example.
Correct. I just picked it as an arbitrary acid that everyone's familiar with to do this. Yeah. It could be any acid. Now, these here are known as neutralization reactions. Okay. And they are generally exothermic. Okay. So when you produce salt and water, it's a neutralization reaction and it is considered exothermic. That's a tie back to topic 5 and 15. So if they give you a neutralization reaction and they ask you what the sign of delta H is, you would say negative. Always. Okay. Questions? Okay. Wait, oh, you still need this? You good? Okay. How do I want to do this? make this a table. Okay, I'm gonna do this. This is gonna be our this is gonna be a table. Okay, and I'm gonna break it up into, I guess, 5 columns. You may want to make it wide if you want to. Now, it's gonna be close. No, I think you're right, kind of big. No, I wouldn't. Yes. One, because I haven't actually figured out exactly what I'm gonna write in here, and 2, you also write very big. You write big. Okay. Weak acids, strong bases, and weak bases. Okay. Don't necessarily, well, some of them, I'm not sure yet. I wish I could tell you. Yeah, you probably want to do it horizontal. Okay. But I'm not sure yet. Now, the reason why I'm not drawing lines all the way down is because some of them will overlap. Like the definition will overlap across 2 of them, and so I'm just gonna save myself a little bit of space for that. So, okay. So strong acids, weak acids, strong bases, and weak bases. Okay. We're gonna have quite a few things here. So, okay. Definition. What's wrong, Camilla? I would start a new page. Okay. Yes, because it's just gonna be wider. Okay. Definition. Okay. Now, both strong acids and weak acids donate NH plus. Okay. That's the definition of the acid part of a strong acid, weak acid. The difference is a strong acid dissociates 100% into ions. And that's kind of redundant, but I just want to make sure when you look back at it that you remember what dissociate means. Whereas a weak acid only partially dissociates into ions, which is usually like less than 1%. Okay. Your bases accept a hydrogen, but again, the strong base dissociates completely, and the weak base dissociates partially. Okay. So understanding definitions for this. Okay. So a strong base would be a species that accepts a hydrogen but dissociates completely in water as well. A weak acid would be something that donates an H plus, but it only partially dissociates in water. Okay. Reaction. Yes, this is all in water. No, no, we won't need to worry about that. Okay. All right. The reaction. So writing a reaction of an example strong acid, weak acid, strong base, and weak base. Okay. Um, I'm going to use HA as my generic acid for this, so that way I don't have to use formulas here. But an HA should dissociate with a single arrow all the way into its ions of H plus and A minus. A weak acid gets the double arrows because it does not dissociate completely. So there is a large amount of HA and very little amount of H plus and A minus in your solution. Okay. For base, I'm going to use the letter B. Okay, a strong base generally has an OH attached to it, and it'll separate into the two ions. Whereas a weak base reacts with water to form the conjugate acid and OH minus ions. And in higher level, we'll talk about these weak acid and weak bases calculations as well. But for standard level, you do not need to know that. Okay. Examples, okay? For IB chemistry, the three strong acids, yes, Marina? Oh, because that's the only one where it's required because that's the only way you get the OH produced. Like all the other ones, they can kind of dissociate themselves, but with a weak base, you have to have water present to act as the acid for it to react. You could actually technically, sometimes you'll see people do the weak acid with it as well, and they'll do this. That's the same thing. Yeah, but yeah, with the weak base, you need the water there present to be able to explain it. Yes. Wait, what do you mean focusing on the products? Oh yeah, because yeah, you do need a source to accept the hydrogen from it. So that's the water. Yeah. Okay, examples for higher level. I mean, sorry, not high level. For strong acids, all levels need to know these three: HCl, HNO3, and H2SO4. Like I said, in college, you'll need to know HBr, HI, and HCl4, but not for the IB. But I write them down here anyways because some of y'all may be taking your notes to college. It's happened before and it'll happen again. Okay. Those are the ones you need to know for college, not for IB. Yeah. With weak acids, it's all the other ones. So all other acids. Now, specifically, I would say the ones you see the most are things like HF, HCN, and ethanoic acid. These are the most popular ones of weak acids that the IB uses. Okay, HF, HCN, and CH3COOH, or ethanoic acid. Okay. Your strong bases, group 1 or 2, hydroxides, and oxides. So any group 1 metal or group 2 metal bonded with O or OH is considered a strong base. Other than, let me say this. I don't know how picky they're going to be here. Not Mg and Ca. Like those are the exceptions. Magnesium and calcium hydroxides and oxides tend to not be strong. Yeah. Okay. The weak bases, usually what you have is really NH3, ammonia. That seems to be the most common weak base, but also you can include things like hydrogen carbonates, and carbonates as well. So those are all classified as weak bases. They accept hydrogens, but not very well. Okay. 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 Equimolar properties. Equimolar translates to same concentration. So these are the properties when you have the same concentration of all these solutions. Because you can only compare things when everything else is similar except for one characteristic. And so we're assuming that all of these in this example have the same concentration so that we can compare them. Okay. The strong acid would have high conductivity. Okay. Fast reaction rate. Okay. Equimolar means same concentrations. Equi meaning same, molar means molarity or concentration. So these characteristics that I'm listing here are only able to be compared if they're all the same molarity, which the IB states in the question. They'll say equimolar. You're welcome. So, because like pH depends on the concentrations, you can make a weak acid have a lower pH than a strong acid if you have a high enough concentration. So, like this only works when you're comparing the same types, same molarity of solutions. The weak acid will have a low conductivity. It will be still conductive though. It'll have a slow reaction rate. And it'll have a higher pH, but obviously still less than 7, not like 11. It'll just be closer to 7 than the lower pH. And you want, oh, sorry, yes, Marina. Strong acids and weak acids. That's a good question. So you, for strong acids, you shouldn't really be able to tell the difference in their properties between HCl and HNO3. They should have almost the same properties. So this is for comparing strong versus weak. Now, technically, you could compare weak ones, but they're not going to have you do that on the IB. But yes, this is comparing versus each other, which is what we're going to say next, because these two characteristics are the experimental techniques to differentiate. So, like if they ask you state and explain one experimental technique used to differentiate between a strong acid and a weak acid, you could say one, I could measure conductivity of both solutions, and the strong acid should have a high conductivity, the weak acid should have a low conductivity. Or I could say, I'm going to react both of these with a carbonate. The one that reacts more quickly or more vigorously is my strong acid. The one that reacts more slowly is my weak acid. But remember, anytime they give you that type of question, you have to address both species to get the credit. You can't just say, oh, this one will have a higher conductivity. You have to say, this one will have a higher conductivity, this one will have a low conductivity. So be careful. Yes, Marina?
You can't say like, oh, the strong acid will have all the products and then
No, because what they're, I see what you're saying, but what they're saying is there, how would you be able to detect it in a lab? So like you actually have to be able to quantify it. So it's not just saying, because what they'll say is like, here are two beakers that are unlabeled, and one has a strong acid and one has a weak acid with the same molarity. To state how you would differentiate them. So you couldn't see whether it has more ions in it, but you can do that based on conductivity, because the conductivity should tell you how many ions are in there. Oh, you just look at how quickly the reaction occurs. So if you react like an acid with like a metal or a carbonate, you'll produce a gas. The strong acid should produce that gas more quickly, the weak acid should produce it more slowly, but it should produce the same amount of gas just over a long period of time. Because the moles aren't different, it's just the number of ions available to react right away are different. Well, it has less available there, but as it reacts, it starts filling in the void of the ones that are left over. So like, even though they're not all free at once, the free ones react, and then the equilibrium shifts to make more ions. So like, yeah, let me just visualize it here. So like, for example, this is kind of a throwback to topic 7. So when it reacts, this goes down, right? But then what happens is the HF will dissociate more to make up for that loss, and it keeps doing it until it runs out. That's why it takes so long, but that's why you also still make the same amount of gas. Because it's all there, it's just not accessible at first, and it becomes slowly accessible over time. That's a good question, because I think a lot of students struggle with that because they just assume a weak acid will make less product because there's less free ions. But what you care about is the total ions to determine how much you react. It's not the free ions determine how quickly it reacts, but not how much it reacts. Okay. All right. Now, for bases, there's a lot less comparisons here. Really, you can only do high conductivity and high pH, and weak acids have low conductivity and lower pH, closer to 7, I should say. Okay. The reason why I didn't circle pH is usually on the IB questions, they usually say, other than pH, state how you would be able to differentiate. So I don't even leave pH as an option because they'll usually rule it out anyways. I guess it's also possible they could ask you to compare a strong acid versus a strong base. But you couldn't do conductivity there because strong acid and strong base should have the same conductivity. So you have to do something like a reaction, like you'd have to add something to it, and whichever one reacts with it, that would be your acid. Yeah, Chloe.
If you were to specify like one of the solutions that like the indicators.
Yes.
If you were to specify an indicator rather than
No, that's still considering pH. Yeah. So that's a good question. You couldn't say adding phenolphthalein or adding universal indicator because that implies you're still measuring based on pH because the indicator only changes color because of pH. So don't use indicator as well. They'll rule that out. That's a good point. Okay. Questions? Let me just make sure. Let me think. You're right at the bottom. Oh, God. Let me just make sure. I don't want to let a good table go to waste. Hold on. Well, won't be the first time, won't be the last. Okay. Yeah, that's the end of the table. Okay. How much space did it take on your paper? Yeah, that wasn't going to fit on half a page. Yeah, y'all wrote it a little smaller than Alexandra does. Okay. We got a couple more things for SL, and then we'll take a little bit of a break. Okay. Okay. All right. So, pH scale. Okay. That's not a title. I'm just kind of breaking up. Still SL, sorry. I save the real titles for class, okay? I don't do funny titles in Saturday sessions. I don't have humor on Saturdays. Okay. No, because you have to do acid deposition too. You can do pH under there if you want. Yeah. Okay, pH scale. So SL and HL, again, a difference in complexity. For SL, you need to focus on the fact that pH means, I'm going to write means so it doesn't confuse, means the negative log of the H plus concentration, or some people, I've heard conflicting reports on whether it actually means power of hydrogen and stuff like that. So it just means negative log of. Lowercase p means negative log of every time. So it doesn't matter what you're talking about. If you see a lowercase p in front of something, that means negative log of. So if it's pH, it's negative log of H plus. If it's POH, it's negative log of OH minus. Okay. And you can also rearrange this to solve for the H plus concentration given pH, because you can bring the negative over and get your concentrations from pHs. Okay. Yes, Marina. Oh, yeah, yeah. Okay. I know where you're going with that, and that's what we're going to talk about in a little bit. Okay. Yeah, because we'll talk about like the pH scale itself. Okay. Because I know where you're going with that. So also what you need to know with this, because everything's based negative log, that means, actually, maybe I should just go straight to the, actually, we'll draw the scale here. Okay. I haven't forgotten your question, Marina. I'll talk about that after we do the scale here. Okay. So our general pH scale is from 0 to 14 at 25 degrees Celsius for our purposes here, our kind of standard conditions. Okay. Now, please remember though that acid is not defined as less than 7 pH. An acid is defined as where your H plus concentration is greater than your OH minus concentration. And those two things are always related to each other in water solutions, which is what Marina was asking a little bit earlier. Okay. A basic solution is one where the OH minus concentration is greater than your H plus concentration. Does that happen to be relative to 7 at 25 degrees Celsius? Yes, but you shouldn't use that as a definition because that's not always true, especially if you're in higher level. At 7, your H plus concentration equals your OH minus concentration. And that's what we call neutral. And you should remind yourself that water is always neutral. Okay. Water is always neutral. There's always the same amount of H plus and OH minus ions in the solution of pure water. A little bit. There's a little more. Because the idea here, Marina, which I'll talk about in a second, is that because everything's in water, water's ions dictate how much of each you can have. And so when you increase the H plus ions, you have to decrease the OH minus ions, and you have to calculate that, which I'll show in a little bit. Now, what you also have to understand is that every unit of pH is a factor of 10 concentration. Okay? So if I go from a pH unit of 4 to 5, there's a difference of 10 times of concentration, actually less in that case, because it's becoming less acidic. So this is, if you want to think about it, this is 10 to the negative 4, and this is 10 to the negative 5. So notice it's a power of 10 difference between the unit here. Okay. Oh, molarity. Yeah. Okay. Apologies of those watching the YouTube video about the construction noise. I'm getting a new pool built in my backyard. and so they can only come on Saturdays. It's really annoying. Okay, they're having the gold chipped in later to plate it, and so apologies for the noise. Yeah, that's true. It feels like home here. Like I should just like have a cot, just put it back here and just sleep here. Okay, so remember, every unit of pH is 10 times the concentration change. So if you go from 4 to 6, that's 100 times difference. Okay, so keep that in mind. That's a common popular SL multiple choice question. They'll say, by what factor does the concentration change when the pH goes from 6 to 4? You'd say a factor of 100 because it's getting bigger. Oh, it's okay. Just oh, it flickers all the time when I'm powering it up. It's okay. Wait, just did it go away or did it? Okay, hold on. Sometimes when it's charging, it acts up with this adapter. Okay. Okay. So remember every increment of pH is that. Now the last thing, or a couple of things here. Oh, let me add this too. Okay. So pH can be measured quantitatively by a pH probe or qualitatively by universal indicator. Okay. Yeah. Yeah, I didn't say which direction it was, but yes, it would be 100 times less or 100 times greater depending on which way you're going, correct. So pH probe can measure the value of it. A universal indicator is a special chemical that changes color based on pH. And so if you put a drop of universal indicator or something, it will change color based on the rainbow, what pH it is. So if it's orange or red, it's an acid. If it's green, it's neutral. If it's blue or purple, it's a base. So it's not a specific number, but you can kind of get a general idea. It's like, oh, this is an acid or this is a base. A lot of times when like we have chemicals that end up not being labeled in the storage and we're trying to clear them out, we'll put a drop of universal indicator in them to see if they change color to know whether it's an acid or a base. And so very useful if you're just trying to figure out whether it's an acid or a base, but not the actual pH. Okay. Now, the thing that Marina was asking about with water is that at 25 degrees Celsius, which is what SL always does everything at, is the concentration of H plus times the concentration of OH minus is also always equal to Kw. And for SL, that's 1 times 10 to the negative fourth. Okay. So if you're in a water solution, if you increase the H plus concentration, you have to increase the OH minus concentration. Both of them can't go up at the same time. They have to be inversely related to each other. They always have to be equal to this. Yes, Marina. Kw is how much water dissociates into H plus and OH minus on its own. Pure water. You're welcome. And that is called, this is called the ionic product constant. It is found in your data booklet, so you don't need to memorize that. For SL NHL, it's in your data booklet, so you don't need to memorize that. You should know that equation is true. What I think you were thinking about is I also showed that if I take the negative log of both sides of this equation, then I get a formula that you might be familiar with from 10th grade or 11th grade, where negative log of H plus is represented as pH. And when you multiply things in logs, what are you actually doing? Adding. So it's plus, what's negative log of OH minus? POH. And that equals, what's negative log of 1 times 10 negative 14? 14. So that's where that equation comes from, which is something you might have learned in 10th grade, is that pH plus POH equals 14. That comes from this equation, and it only works at 25 degrees Celsius for SL, so it'll always work. For HL, it depends. Does that clarify things, Maria? Oh, you're welcome. Okay. So I think that's what you were thinking about when you were thinking about water and the H plus and OH minus. Now, the thing is, I don't believe the IB gives you this in your data booklet. The only equation the IB gives you is pH equals negative log of H plus. So you have to kind of be able to figure out these other equations based on your knowledge of this. So you do want to know these equations. Okay. Questions? Okay. Last thing for SL before we take our break. Okay. Time flies when you're having fun. Okay. Okay. Acid deposition. Okay. This is kind of the real world application of acid bases. Remember, there's like 4 or 5 different real life applications of chemistry spread throughout, or actually environmental chemistry, I should say, that are spread throughout all the curriculum. There's acid deposition, like acid rain. There's the ozone layer for higher level. There is oh yeah, carbon emissions for incomplete combustion, and there is oh, I thought there was I'm trying to think, because I think ozone is just higher level. Um, and then this acid deposition here. So there's a couple of different places here. And so just to review, okay, rainwater is naturally acidic, pH of 5.6, because CO2 is dissolved in it. So it's not that rainwater is neutral and then it becomes acidic and that's dangerous. No, rainwater is already slightly acidic and that's okay. Acid deposition is rainwater that becomes more acidic than 5.6, and that's the environmental damage that can occur from this. Okay, so acid deposition is when you have a pH of less than 5.6. Okay. Okay. You've got 2 kind of major sources of your acid deposition. Okay, and they are your nitrogen oxides. Yes, and these are your NOxes, and then your SOxes, sulfur oxides. Okay. Yeah. So what you want to focus on here is how these things react with water to form acids. And so sulfur oxides like SO2 or SO3 will react with water to form their acid counterpart, which is H2SO3 or H2SO4. Those are kind of self-explanatory. You just combine them. The one that ends up being tricky is NO2, which is one of the most common NOxes, will react with water to form actually 2 acids. Okay. Okay. And I would say memorize this equation, because you can't really kind of figure this out on the fly. You either know it or you don't. So, and that's the one they generally ask about on the test. Mateo. No, it is neutral, because S has a different oxidation number in each one. So yeah, and this is kind of where, that's a good question, that they might tie in topic 9 into this as well. Because what they'll do, Mateo, is they'll ask, well, what's the oxidation number on this S in this reaction, and then what's the oxidation number of the S on this reaction? Because in here it's +4 to +4, and here it's +6 to +6. So there's no oxidation reduction reaction occurring. It's just a normal reaction, a synthesis reaction. So yeah, the oxidation number stays the same. Okay. Now, you could also, I don't know if I don't think we went into detail about this, but you do want to be familiar a little bit with these combustion reactions that occur to make NO2 and things like that. And so what you might see is something like this. So how N2 nitrogen gas reacts with oxygen to form NO2, and how sulfur will react with O2 to form SO2, and SO2 will react with sulfur to form SO3. I don't think I went over these because I think you were supposed to kind of go over this in topic 3 last year when you did like group 3 oxides and stuff like that. So I'll do that in our review session, but uh, hopefully those aren't too unfamiliar. But I'm putting them down here as well. That's all I look like. Okay. Sources. Okay. So remember, there are naturally occurring sources and there are man-made sources. So natural, okay, decomposition of plants. Okay. But man-made, oops, this is the internal combustion engine. Because even like in the best engines, they take in air to create combustion. Nitrogen is one of the things in air. It's the most predominant thing in air. It's like 74% of air. So there's a natural occurrence of some of the nitrogen also being combusted along with the fuel, with the intense heat and stuff like that. So the man-made is combustion engine. For sulfur, natural, volcanic eruptions, and man-made, coal burning. So burning coal, because when you mine coal, it's not pure coal. It has sulfur deposits built into it. Okay. Almost done. Okay. Now this, I know it's starting to look like a table, but this last row isn't actually a table. I'm just going to kind of put all the information just right underneath it. But with sulfurs, you have to know how to remove sulfur from coal burning and stuff like that. So pre-combustion, you just remove the sulfur. Post-combustion, use chemical scrubbers. So something like CaO, calcium oxide, will react with the sulfur dioxide that's produced to form CaSO3, which can then be collected and removed from the exhaust gas that is produced when you burn coal. So the CaO is sprayed in there in a solution form, mixes with the SO2, brings it all down with it, and so it prevents it from being left out into the atmosphere. Now, the thing I'm putting over left isn't just for nitrogen, so I'm going to change color here so you can kind of visually see it, but you do want to know some of the general reactions of acid deposition, like with the environment, okay? And so you might see something like, let's see, like magnesium reacting with nitric acid to form um, magnesium nitrate and H2 gas. Or you might see something like calcium carbonate reacting with sulfuric acid to form calcium sulfate, and then water, and then CO2. Okay. So they said you should be able to write reactions of acid deposition with reactive metals, and carbonates. So this is a big one. Calcium carbonate is known as limestone. That's something that's used in a lot of sculptures and stuff like that, and a lot of statues, and that's why they get damaged by acid deposition, because over long-term exposure to acid deposition reacts with the calcium carbonate and destroys the structure of it and just chemically erodes away. Okay, right about an hour. Okay, that is SL's topic 8 acid base review, and we're going to take a 10-minute break and then we'll start the SL, but I'm going to pause recording right now. All right, so HL. Okay, so HL chemistry takes the concepts of acid and base and takes it a little bit further with additional definition of acid and base. And so in HL, we're introduced to the concept of Lewis acid and base. Okay, so a Lewis acid and base is a different definition of acid and base and a more encompassing definition. So this definition incorporates all acids and bases that we define currently. Okay, because this is more inclusive. So a Lewis acid is a lone pair acceptor. Okay, so instead of a proton donor, it's accepting a lone pair of electrons so that it can donate a hydrogen in some cases. In some cases, you don't even need a hydrogen at all. That's the kind of limitation with Bronsted-Lowry is for Bronsted-Lowry, for an acid to be an acid, it has to have a hydrogen. And there are many acids out there that aren't hydrogen donors or acceptors, and that's where Lewis acid definition comes into play. A Lewis base is a lone pair donor. So it feels the opposite, but it's actually the same in just a different perspective. And it's a better perspective because everything has electrons, and electrons are always being transferred between species, so this definition always applies. Whereas Bronsted-Lowry, you have to have an H plus for anything to happen. Okay. And so to show what I'm kind of talking about here, now that we've talked a little bit about arrows and things like that in organic chemistry, all Bronsted-Lowry acids and bases are Lewis acid bases. So keep that in mind when you're kind of thinking about the grand scale of things. And so like if you're doing like, sorry for the math, like diagram. But Lewis incorporates all Bronsted-Lowry, okay? And so I can demonstrate using a Bronsted-Lowry acid and base how this is defined. So for example, and I'm gonna draw this in a structural format so you can kind of see what I'm saying. Oops, that H kind of. These two reactants here, HF, a weak acid, and H2O, a strong, a base, not a strong base. So what happens here is this lone pair takes this hydrogen from the HF. But that means this lone pair of electrons is allowed to return back to the F because it's no longer needed to be shared. Okay. And so if you think about it, the water is not only accepting a hydrogen as a base, but it's also donating a pair of electrons so that it can happen. Okay, so that's why the definitions are kind of similar. So this is your acid, and this is your base in terms of Bronsted-Lowry and Lewis acid and base. Okay. Now, where it gets difficult is when you have species that aren't Bronsted-Lowry acid bases, and these are generally what we know as complex ions. Okay. And complex ions are ions that are made up of several species kind of bonded together. Okay. And so what you might see is something like this. Cu2 plus 4Cl yields CuCl4 2 minus. This is a little bit of topic 13, so I understand if you really haven't seen this before, but I'm going to put this in the review so that if you watch this video later after we've reviewed topic 13, it'll make a little more sense. Okay? Yeah, sure. Okay. So this doesn't look like an acid-base reaction with Bronsted-Lowry because there's no H being transferred. But when you actually look at what's happening here, the Cu's positioned in the middle, and each Cl with its negative charge is donating a pair of electrons to bond with the Cu, which is how that CuCl4 2 minus species is formed. Okay. And just as a reminder, when you have one species donating both electrons to form a bond, that is a coordinate bond. Okay. When a species donates both electrons. Okay. So in this case, if Cu2 plus is accepting that pair of electrons from Cl, that's our acid. And if Cl is donating, that's our base. Okay. Now, to tie into organic chemistry, I know grown, but Cu2 plus we would consider electron deficient because it's accepting electrons. Okay, it's electron deficient. So what we call this is an electrophile. Okay, so Lewis acids are also electrophiles in the context of organic chemistry, and bases are nucleophiles because they're looking for a positive charge to bond with, and so Lewis bases are nucleophiles. Lewis acids are electrophiles. Generally speaking, if you have metal ions, they're going to be acids because they don't have valence electrons, so they can only accept electrons. So this is usually, acids are usually metal ions. I say that, but there are a couple of exceptions to that of sub-octet species. Okay. So there are some Lewis structures that have less than an octet, which can accept a pair of electrons, namely these two here, BF3 and AlCl3. Because when you draw BF3 out, you notice it only has 3 bonds and it has an opening to accept a pair of electrons. AlCl3 is the same way. So these are both Lewis acids. Okay. So if you see two species combining together to form a new bond between them, that's generally a Lewis acid-base reaction. Whether it's forming some complex or whether it's just forming a new bond between them, it's going to look like a synthesis reaction, I would say. A Lewis acid-base reaction looks like a synthesis reaction. So Lewis acids are metal ions and also sub-octet species like BF3 and AlCl3. Bases are anything that has a lone pair of electrons, essentially, that can donate it. Oh, I wanted you to group the idea of Lewis acid with electrophile and then Lewis base with nucleophile. You're talking about the green circles, right? Oh, sorry. The red circles, that's the empty pair of electrons that can be accepted. So like, sorry, the red circle is like, that's the empty space that allows it to accept another pair of electrons. Sorry. Suboctet species means it has less than an octet, which means it has less than 4 pairs of electrons attached to it. So boron and aluminum, because they only have 3 valence electrons, only bond 3 times usually, which means it only has 6 electrons owned. So that means it has space for 2 more electrons. Does that make sense, Camilla? Kind of. Because remember, every species wants to have 8 electrons, right? The problem with boron and aluminum is because they don't have enough valence electrons, they can't bond 4 times on their own. They can bond 3, and that means it needs something else to come in with both electrons to bond that 4th time. And so that's why I circled this space up here, because that's where the fourth bond could go. Oh, because acids are metal ions and then plus suboctet species. So Lewis acids include metal ions and suboctet species. I just ran out of space. I didn't plan very well on my paper. Okay. Yeah, the metal ions are included in acids, and then so are suboctet species. Correct. Now I did that first because that's the only context really of Lewis acids and bases that you need to know. Everything else is related to Bronson-Lowry and related to HL/SL stuff like pH and titrations and stuff like that. Okay. Questions? Okay. HLPH calculations. Okay. For HLPH calculations become more complicated because now you have to factor in Rice charts because you are going to have partial dissociation, and you are not going to have like strong and acids and bases alone. You have to understand that weak acids and bases partially dissociate, which means they have a K value, which means you have to do a Rice chart, which means you're going to be very sad. Okay. Just on the cart. So weak acids and bases are partially dissociate, which means you have to use K values in which you have Rice. And so that is where Ka and Kb appear. Ka is your acid dissociation constant. And Kb is your base dissociation constant. Okay. And they're labeled that way because that's how the species being described behaves. And so, like, if I wanted to see the Ka, yeah, of HF, what I'm implying is that HF is going to act like an acid. let me unmute. When I say Ka, let me make sure I'm recording. Okay. When I say Ka of HF, that means HF is acting as acid. So I wrote the reaction of HF next to it, which means the Ka expression is H plus times F minus over HF. Yes, Ka. Okay. And that's really important for the rice chart because you have to understand what the expression is so that you can plug in variables and solve for things. Okay. So if I were to do a rice chart here, I would do it like this, probably plus x, and minus x. And then I have to solve for x. But in these cases, I would use the 5% rule because Ka is very small. So you could approximate by ignoring what the minus x and the minus x is. So these are your rice charts. Okay. I don't know if everyone would agree with you there. Okay. Now, also understand that pKa, based on your knowledge that we talked about earlier, what do you think pKa stands for? Negative log of Ka, right, Mateo? And pKb is negative log of Kb. So you may have to rearrange things to solve for Ka and Kb based on your pKa, just like with pH and pOH. Ka would be 10 to the negative pKa. Kb would be 10 to negative pKb. So you may have to rearrange this equation around to be able to solve for a Ka or Kb that you can use for a rice chart. Because in the IB data booklet, everything's given as pKa and pKb. Let me show you that here. So like, let's see. Oops. So if you look at a data booklet here and you look at the acids and bases, you'll see that they give you it all in pKa. So you'll need to convert. And what's nice is, and we'll talk about this next week, is in your get to know your data packet, they actually give you the equation for pKa. So like, you shouldn't forget what that is because it's given to you in the data booklet in this section where it's appropriate. And pKbs are the same idea. Just read closely. Like the bases down here are pKbs. Okay. So you do need to know how to convert between pKb and Kb and pKa and Ka. Now, let's see. What also is important is that for a conjugate acid-base pair, so the Ka of an acid and the Kb of its conjugate base, or Kb of its of its base, and Ka of its conjugate acid, those two values end up equaling Kw when you multiply those Ks together. So the Ka times Kb of a pair always equals Kw. Okay. Now Kw depends on temperature, but at 25 it's 1 times 10 negative 14. But what this is important for is because if the Ka goes up, the Kb has to go down, which means if you have a stronger acid, you have a weaker conjugate base, and vice versa. The weaker the acid, the stronger the conjugate base. And this only has to do with weak acids and bases. Like strong acids and strong bases are completely way off the spectrum on both ends, so we're not really comparing those. Like if you're given a strong acid and any weak acid, the strong acid wins in the strongest like acid most associated. And it also has the weakest base by far. So this is just when we're comparing kind of weak acids with each other. So the stronger the acid, the weaker the conjugate base. Now, one of the things that you need to know is identifying how strong a weak acid or weak base is, okay? So we've already established that the larger the Ka, actually the larger Ka or Kb, let me not write it that way because it looks like divide. The larger the Ka or Kb means stronger, which means it dissociates more, okay? So if I'm looking for larger Kas or larger KBs, I'm looking for smaller negative exponents because all of them are negative exponents. So you need to make sure you understand that 4.5 times 10 to the negative 4 is greater than 9.0 times 10 to the negative 5. Okay, pay attention to those negative exponents. So this is the stronger one. Okay, but you also need to understand, if I give it to you in terms of pKb, it's also kind of backwards because pKb is negative log. And so if I take the negative log of this constant, this Ka, because it's a negative log, it does the opposite relationship. So if I do negative log of 4.5 times 10 to the negative 4, I get the pKa of 3.35. And if I do the negative log of 9 times 10 to the negative 5, I get 4.05. So this is still stronger though. So you do need to know that the pKa relationship is the inverse of the Ka relationship. So if the Ka is bigger, you're going to end up getting a smaller pKa because you're dealing with negative exponents here. So the pKa is kind of the opposite. Huh? Yeah, it's an inverse relationship. So the smaller the pKa, the larger the Ka. The smaller the Ka, the larger the pKa, which then tells you which one's stronger regardless. So the smaller the pKa, the stronger the acid. The larger the Ka, the stronger the acid. Ka. And same with Kb. The larger the Kb or the smaller the pKb, the stronger the base. And when I say stronger, I mean dissociates more. That's the emphasis here. Okay. Looks like they're installing my buckyball water fountain next to my pool. It's just this giant C60 molecule that just spits out water everywhere. Yeah. uh, it's a very chemistry themed backyard I have. Yeah, I know. Okay. I have a coal mine built in too, and then there's a canary that kind of just flies in and out sometimes. Sometimes it doesn't fly out. Yeah. Yes, that's right. Why am I recording this on YouTube? I shouldn't be recording this joke on YouTube. Now they're like, PETA's gonna come after me. I don't actually have a coal mine where I let canaries die, for the record, yet. Okay. All right. So understand that relationship between those ideas. Okay. All right. We're actually making pretty good time here. Okay. What this leads us to, so this is all determining pH and pOH of weak acid, weak base, all the rice charts, stuff like that. I'm not going to go do practice problems with that. You have enough to kind of look back at that for later on, which we'll talk about. Well, not for today, but we'll use that in kind of review sessions. The next part is essentially pH curves and titration. Oops. Okay. So pH curves and titration. So titration is the experimental process. pH curve is the result, the data that you collect when you titrate. Okay. So this requires a neutralization reaction. Okay. And the idea is that for this to work, you assume that the moles of H plus in your acid are equal to your moles of OH minus in your base. Okay. Excuse me, that was my stomach. Okay. All right. Okay. Yeah, I didn't realize that was open. Put your weight into it, Mateo. Okay, that helps a little bit. No, I think I closed that one already. It's just like really right next to it. Yeah, yeah. They're cutting through concrete, I think. Yeah. I don't know. I think they're just reconstructing the concrete slab over there. I don't know if it's like collapsing because the foundation's like needs to resettle or something like that, but I don't know. They don't tell us these things. It's above my pay grade. Okay, so the moles of H plus equal the moles of OH minus when it's neutralized. And so it's important that when you you need to write a balanced reaction for an acid plus a base reaction. So like, for example, you might see HCl plus NaOH yields NaCl plus H2O. This is a 1-to-1 ratio. So that means the moles of HCl equal the moles of NaOH when they're neutralized. But you could have a reaction where the coefficients aren't the same, and then you'd have to factor that into your equation. Okay. Oh no, you can. We're not doing that yet. Okay. So at this point, it's a stoichiometry problem. You're converting from your moles of your. So you need to know these kind of calculations. You need to know one, molarity is equal to moles over volume in decimeters cubed. Okay. Two, you need to know your mole to mole ratio, your moles of base to your moles of acid. Okay. Actually, those are the only two things you need to know. You just need to use molarity twice. So these are the two calculations you have to be able to do to go from the concentration and volume of one species to get to the concentration or volume of the other species. Those are the only two calculations you need to know. And you just have to use them in order to get to the right value overall. Okay. Bless you. Now, before we do pH curves, we're going to talk about salts briefly here because I think that's kind of important before you do pH curves. Oh, that's the mole to mole ratio. So like, if this would be 1-to-1 in this example because it's 1 mole of NaOH for 1 mole of HCl. Okay. Let me erase that so people aren't confused. This is your mole to mole ratio. Okay, salt and pH. Okay. You don't have to know the exact pH of a salt. That's not what they're talking about. They want you to be able to generally identify, okay, this salt came from this acid and this base. What pH should my salt produce? And so it depends on the strength of the acid and base that it came from. So for example, when you have NaCl, what acid and what base did NaCl come from? What acid and what base forms NaCl? HCl and NaOH. And it turns out both of these are strong. This is a strong acid and this is a strong base. So a strong acid plus a strong base makes what kind of salt? What kind of pH salt? Neutral. Acidic, basic, or neutral are your choices. So strong and strong makes neutral. Because when these salts are formed, because they are conjugates of strong acids and strong bases, they don't recombine together because they dissociate completely. So like the idea here is that if I add NaCl with water, theoretically I should make HCl and NaOH, right? But the problem is when this happens, because these are strong, they dissociate anyway, so they don't actually ever form. So then you're just left with NaCl. That's why it's neutral, because there's no OH or H plus being formed because the original acid and base are too strong for it ever to be reformed. Okay, you're welcome. Now, if you have something like NaF, what does NaF come from? HF and NaOH. You just usually add OH to the first species and H to the second species. So HF and NaOH. So this is a weak acid and a strong base. Okay. So you end up with a basic salt. The strong part, the strong parent, or the strong acid or base that it originates from dictates what type of salt you're going to have. Okay. But if you were to try to write this out like this, you would get HF plus NaOH. And the NaOH would dissociate because it's a strong base. And that production of OH minus is what makes it basic. Because some of the HF will reform because it's weak, so the F minus will bond with the water to form HF and then also form NaOH. OH minus as well, and that OH minus is what gives it a basic pH of the salt. So if you're just trying to figure out whether the salt is acidic, base, or neutral, just look at the original acid and base. If you're trying to justify it, you have to write the reaction out and then show that you're producing OH minus or show that you're producing H plus as a product. And vice versa. If you have something like NH4Cl, that comes from NH3 and it comes from HCl. This is a strong acid, weak base. So therefore, this is an acidic salt. Questions about that? So just think about what it originates from, and that dictates what kind of salt you're going to get. Okay. The salt helps us determine the pH of the equivalence point on a graph, on a titration curve, I should say. Okay. And that's where we're going to go next. We're going to talk about titration curves. Yes, because you're probably going to want to draw a big titration curve and label a lot of stuff on it. Yeah, but the first one will be the big one that we'll label a lot of stuff on, and the second one will be a smaller sketch one. You probably should. Again, it's just because you write big, nothing personal. Probably half a page is fine. Yeah. Okay. Sorry. Okay. Because we're going to label all the parts of the titration curve on here, so it's going to get a little kind of cluttered. Okay. So a titration curve has pH versus volume of titrant. here, okay? Titrant is what you know concentration of and what you're adding to your solution. Analyte is your unknown, okay? Not much though. Analyte is your unknown concentration. Titrant is your known concentration. So like, for example, let's say we're titrating here, HF plus NaOH yields NaF plus H2O. And let's say, pretend our titrant is NaOH. Okay. Well, our acid, because we're starting with HF, should start at a low pH. Not a super low pH, but a below 7 pH. And what will happen is something like this. Okay. Remember, the equivalence point is the midpoint of that vertical part. Oh, that did not look very straight. Closer. Okay. And this would be like 7, because remember, a weak acid plus a strong base should yield a equivalence point above 7. So notice that I've drawn that here. Okay. The equivalence point, where there is only salt and water. So you've neutralized all your acid, you've neutralized all your base, all you're left with is salt and water. So you've got ions and water, essentially. Okay. At this point here, the first point, you have a majority of your HF. We'll make the little bar graph here. You have the majority of your HF and a little bit of F minus. Okay, no base added yet. It's just HF sitting in water dissociating partially. Okay. Now, as you add the base, the HF goes down because it's reacting with the base, and you're making more of the F minus. And you get to this special point halfway to the equivalence point, where you've used up so much HF that the F minus is the same amount now. HF and F minus are the same. Why is that important? Because when you think about HF's Ka, it's H plus times F minus over HF. Well, if your F minus and your HF are the same, what can you do to that expression? If F minus and HF are the same, what can you do? You just have H left over. It cancels. So at that specific point, the Ka is equal to your H plus concentration. And also, your pKa is equal to your pH. So at that special spot, halfway to the equivalence point, half the volume that it takes to get to the equivalence point, you have a special piece of information where the pH at that point is equal to your pKa. Uh, okay. So, other points we need to label on here. this point here. This is the volume used for calculations. So the volume at the equivalence point is the volume that you use to do neutralization equations. So that's the volume of NaOH that tells you the moles of NaOH that you react with the HF unknown solution. Okay. Correct. It's coming back. Okay. And again, halfway to the equivalence point, half the volume is where pH equals pKa on this graph. And also, I guess if you really wanted to say it, you could also say pKb is equal to pOH at this point right here. Yes. Yes, all that. Like both these things I circled are both true. Now, one of the ways that we can get a visual cue to let us know that we're getting close to the equivalence point is what we call an indicator. Okay. Okay. An indicator is a weak acid or weak base whose components have different colors as a conjugate pair. Meaning that the acid part has one color and the conjugate base has another color, or the base has one color and the conjugate acid has another color. So there's a change in color when things occur. So like you could write it like this. So let's assume that we have a weak acid indicator. What we assume is that this would be one color and this would be a different color. So when you start titrating and you shift the equilibrium, the color changes. It's like phenolphthalein. Phenolphthalein is an indicator. Phenolphthalein in its acidic form is colorless, but when you start adding base to it and you start getting rid of the H plus, it shifts to the right and turns pink when it's in a base. So the color changes based on the pH of the solution and the environment that it's in. And each of those indicators has a range at which it changes color, and you want that indicator to match up as best you can with that equivalence point. So you want to make sure that the pH of the indicator color change is similar to the equivalence point pH. And so you can see, oh, sorry, make sure, see if anyone else is writing down stuff. Are you still writing? Yeah, keep writing. Huh? No, I'm not, no, I'm going to switch pages though. So. Oh, that works too. So when you look at the data booklet, there is a page of indicators and when they change color. So this pH range is where it changes color, and these are the colors it changes into. So be careful on the data booklet. We'll talk about this next week as well, that acid and alkali don't mean less than 7, greater than 7. What they mean is less than this range or greater than this range. So it's relative to the pH range of this. So acid here means less than 3.1. Yellow here means greater than 4.4. And then in between, what color do you get? What color do you get in between this range? Orange. Did you have to think for a second combining red and yellow, Emma? Okay. So you'll see. Okay, yeah, you're in art. Oh. Oh. Well, some of them do, but like phenolphthalein doesn't say it, and like phenol red is just this red, not like the combination. So like the color in the indicator doesn't necessarily mean it's a mixed color. Like
So we have to actually think about it. Like what is red and blue? Like I don't know. Like what yeah, like
you don't know what yellow and blue make?
green.
It's green.
So like I have to actually think about that on the test. Like check like
Yes.
colors.
I didn't realize that was going to be the hard part of the exam is combining colors. Oh no, it's actually light pink because color just makes the pink fainter. So like whenever you do titrations in like 10th and 11th grade, we always said go for a faint pink. That's because we're kind of like looking for kind of a mix between colors and pink, so it's kind of fainter than usual. Because it turns bright pink when you add too much, like way too much, it turns bright pink. So keep in mind you'll want to choose the right indicator to fit your titration. So if you have a basic equivalence point, you want phenol red or phenolphthalein. If you have an acidic equivalence point where it's less than 7, you want things like methyl orange, bromophenol blue, bromocresol green, and stuff like that. And if it's around 7, you could take bromothymol blue or even phenolphthalein. Technically, phenolphthalein is still acceptable. They'd probably take it. But we'll talk more about these colors later on when we talk about get to know your data packet next week, because that's something we'll have to talk about. But so just keep in mind that this range is where these colors change, not based on 7 for these indicators. And usually when they ask you select a suitable indicator, they'll take more than one answer. Like they'll take, you don't have to say methyl orange or bromophenol blue. They'll probably say they'll accept either one. Or if it's base, if you say phenol red or phenolphthalein, they'll take both. So it's not like one right answer. You could both get credit for it if two people said the different ones. Okay. All right. The last part I want you to label on here, this is called the buffer region. Kind of, yeah. That section here. It's not an exact art, Camilla. Like you don't have to like it has to be from this to this. It's kind of like the part where you have a bit of both species. Okay. Okay. So a buffer is a solution that how do I want to say this? I don't know if I want to say reduces. Um, yeah, that uh, reduces pH change when a small amount of acid or base is added. So what a buffer does is a buffer prevents the drastic change of pH when something's added. So like the analogy that I gave in class was imagine water being white paint and H plus ions being red paint and OH minus ions being blue paint. If I put 1 drop of red paint or 1 drop of blue paint into white paint, it's going to drastically change the color of the solution. But if I have purple paint and I put 1 drop of red and 1 drop of blue, you're not going to notice it because the purple already absorbs some of that red and blue. So it's harder to distinguish that because there's no contrast there. It kind of blends in. That's what buffers do. Buffers have species in them that help you absorb any change that you add into it so that it doesn't have as much of an impact. Okay. And so that's why I say the word reduces and not prevents. Prevents implies that it doesn't change at all, but even buffers change pH slightly. So I say reduces or minimizes pH change. Oh, actually, I remember the word I want to use here. Resists pH change, I should say. Sorry. Resists pH change. Did you really going to start over? Okay. All right. Resist pH change. That's the R word. I just had a mental block. I'm like, reduce? No, that's not right. Resist pH change when a small amount of acid or base is added. Okay. And so what you have to understand is what is buffer action? Okay. So these are the reactions that show the resistance. So like what is the buffer doing to allow it to prevent the H plus or the OH minus to float freely around and drastically affect the pH? Okay. No, okay. So for example, and you have to have something weak on both sides to be able to kind of absorb this, because strong things won't absorb H plus or OH minus because they'll just dissociate again. And so let's say we have a buffer of NH3 and NH4Cl. Okay. So when you dissolve this in water, you're going to have NH3 floating around, NH4 plus floating around, and Cl minus floating around in that species, in that beaker. Reactions, or yeah, reactions. It can be two. It's two, but usually you only have to show one, because one is when it resists the pH change of acid added, and one is when it resists the change of pH base added. So here's your buffer solution. I'm a very visual person. I like to see everything that's in my species. Now, if I add H plus to this buffer solution, okay, what species is going to absorb that H plus so that it's no longer free, but also keep it together? Okay, if it reacts with Cl, what does it form? HCl. And what kind of acid is HCl? Strong acid. So what's going to happen? Is the HCl going to stay together? No. It dissociates. So that's not buffering, because the H plus is going to break off away anyways. And so you need something weak to absorb it. So what is capable of accepting an H in here? What's another base that's in here? NH3. You can't get NH5 plus. There are 2 plus. So NH3 plus. Because NH3 allows you to make NH4 plus. Okay. So the buffer action is NH3 can absorb H plus by bonding with it and forming NH4 plus, which is weak. So not all of it will dissociate. A lot of it will stay together. The buffer is essentially a weak conjugate acid base pair in a solution. Well, because when you start combining stuff together, certain things won't work out. Like we said here, which was a good example. I said H plus. Well, you said, okay, bonds with Cl minus. Well, H plus plus Cl minus makes HCl. The problem with HCl is a strong acid. So even if you made HCl, what's going to do immediately? Because it's a strong acid, what does it do? Right. So even if you make HCl, it's just going to break up apart anyways. So that's not buffering. You need something that's weak. Yes, it has to be weak, because it has to somehow bond with it, but not let all of it break apart again. So if I add OH minus here, which part of the buffer am I going to react with? Which species am I going to react OH minus with? Out of this container. No, because NH3 is able to absorb a hydrogen. So it's NH4 plus. Because NH3 is a weak base. That's one of the examples that we gave when we talked about weak bases. Okay. So NH3 is a weak base. Okay. So these are your two buffer reactions that are happening here. Okay. What do you notice about these buffer reactions when you compare them to each other? What do you notice about the reactions and products of the buffer action? They produce each other, right, Emma? So in buffer action equations, your buffer species should always be conjugate acid-base pairs of each other because they should be absorbing to make each other in the reaction. So this is kind of what Camilla was asking earlier, is that a buffer should always be a weak conjugate acid-base pair. So when you draw this solution out and you say, okay, there's NH3, NH4, and Cl minus, there's only one conjugate acid-base pair in there. That conjugate acid-base pair is NH3 and NH4 plus. So that is going to be your buffer action. So you can immediately say, that's my conjugate acid-base pair. One of these is going to absorb an H, and one of them is going to absorb an OH minus to make each other. Like Emma said, the NH3 makes NH4 plus, the NH4 plus makes the NH3. That balance is what allows a buffer to work. Camilla, does that help you? Okay. So for example, let's say I had HF and NAF. Okay. Maybe that's the way we should think about it. Okay. So I'm going to draw it out. The salt NAF is always going to dissociate. So you have something weak and then you have the salt, and the salt's going to dissociate. Uh-oh. Buffer action. Okay. What's our conjugate acid-base pair in this mixture here? What is our conjugate acid-base pair? HF and F minus. So identifying that lets us know what's going to be absorbing H plus and what's going to be absorbing OH minus. Okay. So based on that, I have F minus and HF. What's F minus going to be absorbing? What would F minus have to absorb to produce its conjugate? An H. Because when it absorbs H, guess what it forms? HF. So HF is capable of absorbing OH minus to form H2O and F minus. Do y'all see it a little bit more now? So this conjugate acid-base pair has to be able to absorb H plus and OH minus. And one absorbs H plus to form the other, and the other one absorbs OH minus to form the other. So it kind of limits your options here with buffer action because you have your conjugate acid-base pair. One can accept a hydrogen, one can accept an OH to make each other, and those are the only reactions you can have. Questions about this? Yes. Yeah, you'd only ever have to write a maximum of 2 buffer reactions. Buffer actions, they would usually just say, write the equation of this buffer when a small amount of acid is added, which would be the first one, and a small amount of strong base would be the second one. Okay. So identify your conjugate acid-base pair in your buffer. 2, figure out what the conjugate acid-base pair would absorb to make the opposite one. And then those are your 2 buffer action reactions, and then pick the one that the question is asking you about. Are you adding H plus or are you adding OH minus? That's how you come up with buffer action. Okay, let's do one more really quickly. HCN and KCN. Okay. What do we have in our container here? HCN is not strong. K plus. Yeah, HCl is strong. No, because HCN is a weak acid. We're just dealing with things in significant amounts here. So the H plus amount is very insignificant compared to all these. Okay. So what's our conjugate acid base pair here? HCN and CN minus, right, Rachel? Okay. So if you have CN minus and you're trying to make HCN because that's your conjugate, what does CN minus need to absorb? An H plus. Exactly. And if you have HCN and you're trying to make CN minus, you have to absorb an OH minus. Yes. If they say strong acid, you infer H plus. If they say strong base, you write OH minus. Yes. Not in these, you would never have to write them. You could just write H plus, they would accept that. Okay. One last thing, and then we're done for today. Okay. Yeah, we're going. I know we're going kind of quickly through this, but it's okay. This I don't know how this might take 10 or 15 minutes, so it's okay. So yeah, who said wait? Oh, okay. Okay. The last thing we have to talk about is making buffer solutions. This is the one that was kind of giving people fits here because it's difficult to kind of understand how to make them. But the idea is the same, and this is why I drew the pictures earlier, is that the idea is to get the conjugate acid base pair in the solution in significant amounts. So like if you have HCN and KCN, you want HCN and CN minus in large amounts. So there's two ways to do that. One, you could mix HCN and KCN together in any amount. So if I have HCN and KCN, KCN being the salt of HCN, I can mix them together and I'll make a buffer automatically. It doesn't matter how much of each I put in there, as long as I put in an amount of each, I will make a buffer. The trick or the problem is when, let's say I don't have any CN salts. Let's say I don't have NaCN. Let's say I don't have KCN or anything that has CN as a salt in it, but I have a bunch of HCN. Okay. What could I react the HCN with to make the other part of my buffer? Well, no, let's say I don't have any salts. So, but how would I make the salt? If I have a weak acid, what would I need to react it with to make the salt? A strong base. Exactly. So I could mix HCN with a strong base, or I could even write it as KOH if that helps y'all. Because when HCN reacts with KOH, it forms KCN and H2O. So if I mix some KOH in there, I will make some of the KCN that I want. Okay. But what do I have to be careful about? Exactly. There's not too much KOH because if you use all the HCN, then it's no longer a buffer. So the amount of KOH has to be less than the amount of HCN. Exactly. So you have to be careful with that and be careful of mole to mole ratios as well. Because a lot of times it's 1-to-1, but sometimes the IB will put one in that's confusing and it'll be a 2-to-1 ratio or something like that. So you really have to be careful with how much you need. This is the one we spent a lot of time on in class. We're like, how much of this would neutralize with this, and would there be any left over? So that's what we're going to kind of talk about here. So to make a buffer, you can either mix a salt and its weak counterpart together. So you could do a weak acid and its salt, or a weak base and its salt, or you can mix a weak acid with a strong base, or a weak base with a strong acid. But then you have to be careful with how much you're putting in there. And that comes down to the moles. Oh yeah, sorry. There. What, Chloe? Wait, what? Oh, sorry. Yeah, I gotta. It's yeah. You'll have to excuse my brain for having taught and been at the school for the last for way too many hours for the last 2 days. I was trying to do the math. It was like 11 on Thursday, 12 on Friday, and then 6 today. So, but tomorrow's break day. Then we resume things on Monday and Tuesday. Why do I do announcements? Like what? Why do I even do announcements? See, 10 A's got me. Uh, I did for a little bit. I forgot to tell your class for a few days about it, but yeah, yeah. I lose track of what class I've said to which, and so I know. Okay. Oh yeah, the bracelets. That's right. Oh man. Okay. Okay. So how do they ask this kind of question? Well, a lot of times they'll ask like, which of the following can make a buffer solution? And so they'll say something like this, and this is not a multiple choice. I'm going to give you different options. Something, but there may be more than one right answer. But they'll say 50 centimeters cubed. Oh, actually, you know what? We'll do this, okay? Because I want to do the calculation. 50 centimeters cubed of 0.1 molar. Yes, kind of HF, and 50 centimeters cubed of 0.1 molar NaF. Okay. B, 50 centimeters cubed of 0.1 molar HF and 50 centimeters cubed of 0.1 molar NaOH. Okay. And then 50 centimeters cubed of 0.1 molar HF and 25 centimeters cubed of 0.1 molar NaOH. And D, 50 centimeters cubed of 0. Hey, I'm having to write it too, okay? Of HF, and I know. Oh yeah, that's true. I'm just like trying to write as fast as I can. 0.1 molar of BaOH2. I'll give y'all a chance to copy that down before we come. I ran out of space. Stupid happy birthday card. Yeah, I thought about it, but I wanted to make sure that y'all saw it the way it would be on the test. Because they won't write capital M on the test. They'll always write moles per decimeter cubed. So it's okay. So I've given you 4 possible. I'm not going to answer yet. I'm just saying I've given you 4. It's not a one is the right answer thing. It's a each one will do yes or no for this. Okay. And so write this down and then we'll break this down. No, it'd probably be a multiple choice where only one is right. But I want to try to tackle a couple different birds with one stone, and so, um, oh no, yeah, it should be just centimeters cubed. On the last one, I wrote 25 centimeters negative 3. It should just be a lot of things are changing, which we're going to talk about. Okay, so sorry, I'll give you all a second to write this stuff down. Now, of these choices, is there one that is a buffer no matter what? Is there one of these that is a buffer no matter what? Okay, why A? Right. So you have HF and NaF. So it doesn't matter what the concentrations are or the volumes are. This one is always yes. Okay. Now the other ones are, it depends, because we have to figure out, because now we're adding a strong base to each of these. So it does depend. Okay. Because you're mixing the salt and the weak acid together already, so there's no reaction that needs to occur. It just dissociates in the conjugate base. Because NaF breaks up into Na plus and F minus, and F minus is the conjugate base of HF. So mission accomplished. Because remember, to have a buffer, you have to have a weak acid conjugate base pair. And HF is a weak acid, and what's its conjugate? F minus. So do we have a source of F minus? Yes. That NaF. Because NaF, when it dissolves, it forms Na plus and F minus. So that's your source of F minus. Okay. Now, I'm going to move this down just a little bit. Okay. Yeah, BaOH2. Yeah. Okay. Now, the second one is NaOH with HF. Okay. That could technically work, but you have to make sure you have less moles of NaOH than you do of HF. Now, because you have the same volume and the same molarity, you have the same moles of each. And the problem is it's a 1-to-1 ratio, so this is a no, because there will be no HF left, because all of it will react and it'll be completely neutralized. Okay. But in this one, because it's a 1-to-1 ratio, but there's less NaOH moles wise, this one will work, because you have half the moles of NaOH than you do of HF, so you should have HF left over. 1-to-1 ratio. Okay. So let me ask you this. Okay. Why is D difficult? Okay. What about D makes it a difficult decision on this? What?
I think it has something to do with the subscript too. So it's like multiply.
Okay, so you're on the right track, because to identify buffers, you have to know several things, and this is how multiple choices work for the IB. Because a multiple choice question isn't just going to require one piece of information; it's going to require 2 or 3 to get right. That's how they get all the wrong answers as well. So Camilla's right. One of the big things is this is BaOH2, not NaOH. That's the extra step that students at our 5s and 6s may not get and the 7s notice. Because a 5 student for buffers probably knows, okay, I need a weak acid and a strong base. Okay, good. And I know that I need to have less base than acid. Okay, but if they stop and just look at these values here, they'll get it wrong, because like Camilla said, this is BaOH2. Huh? Okay. So, wait, what? So this is times 2 as much base you have here because each of those produces twice as much OH minus. So that means you actually have the same amount of HF as you have BaOH2. And so this one ends up being no. So that's the trick. Again, the IB preys on the fact that students are just going, I just need to memorize it's less volume on the strong acid or strong base, and it's going to be a buffer. And then they throw this twist in, and if you don't understand the whole concept, you'll get it wrong. So that's the IB, and that's why we stress so much understanding the stuff than just memorizing, because memorization causes issues when they give you twists, and if you don't understand it, you can't figure out the challenges in the questions. Okay. Any questions? Yes, Rachel. Oh, because HF and NaOH react in a 1-to-1 ratio. So 1 mole of NaOH reacts with 1 mole of HF. And in this case, in C, you have half the moles of NaOH as you do HF. So you should still have half of this left over. But here, because it's 2-to-1, because there's 2 OHs, that's the same as having 50 centimeters cubed of NaOH, which is then the same. Yes. Okay. We'll stop there and I will upload this later today.